Hello to everyone and welcome to States of AI, the new collection of lectures in my YouTube channel. I am Matteo Ciprian, the owner of this channel, and this series of lecture is intended for a broad audience of tech experts to explain some specific topic related to the AI. Today, we are actually exploring what I would define a use case of AI and machine learning, actually. Is kind of really niche topic, a really peculiar field, which is GNSS. So the lecture today will be around machine learning techniques for GNSS. So for who don't know, I mean, I really hope the concept of GNSS is quite clear, but GNSS stands for Global Navigation Satellite System. Is a term to describe a system of satellites that provide positioning, navigation, and timing. So the most important, most well-known GNSS system is GPS, but we have also GLONASS, Galileo in Europe. The algorithm used in GNSS position is mostly kind of old-fashioned signal processing algorithm, but over the last year, there are people like the guests I have today that are trying to apply kind of more data-driven or statistical analysis to improve GNSS performances. As we will see, to the question, what is the application of machine learning GNSS, is the answer is not straightforward, because as we will see, GNSS is a quite complex pipe, and there is different stages of this pipe, and we can apply at different level different type of techniques. So today we will have a kind of overview of these techniques, and we will see what is the state of the art actually of the application of machine learning in GNSS. So this is the overview of the lecture today. Let's go to my guest. So Ross, welcome to the lecture.
Hi, Matteo. Great to see you.
So just for the first introduction, Ross is a colleague of mine. We both work at the moment at focal point positioning. Ross is an expert signal processing engineer that works with a specialization in signal processing for GNSS receivers. So he has a master degree in electronic engineering at University of Pretoria in South Africa. He has also, in 2023, in June 2023, so quite recently, he has defended his doctorate PhD thesis on GNSS spoofing detection at University of, I will read it, Friedrich Alexander Universität in Erlangen. Have I pronounced it correctly?
Very good.
Perfect.
Very good.
Ross is currently working at Focal Point now as a GNSS engineer, and topics of research include signal processing for GNSS, interference management, and array processing. So I think that I have provided now a kind of overview of the lecture. So Ross, when you want, please start, and we are all here to hear about how we can use ML for GNSS.
Cool. Thank you so much for the introduction, Matteo. So today we're going to talk about machine learning in satellite navigation. So obviously we can't go into super high detail, but I would like to give an idea of how ML is starting to change GNSS. I think one of the interesting things about GNSS is it's a very, very narrow niche and very deep, and changing the traditional ways of doing things is taking some time. But there are already some interesting applications coming out here. So I think the most important thing at the start is to know what is GNSS. Like, why are we talking about this? How does a typical receiver look like? And basically, you have three steps. A satellite transmits a signal. So you can see I have here some examples of a satellite transmitting a signal. Somewhere on Earth, you have a receiver that's receiving it and processes the signal. And then based on this distance between the two, it can calculate where on Earth it is. So this is a very, very big oversimplification. But I think the important thing here is, because you have a transmission delay from when the satellite sends a signal, it takes some time until it gets to us at Earth, which is at the speed of light as electromagnetic signals travel. This time delay results in a distance that you can calculate, and that's how you can get these together. And this is as I said, basic concept is very simple. I think that's all we need to do, so we can go home now. We know what GNSS is. But to really map this a bit closer to what machine learning can do for GNSS, we have to go a bit more deep into how a GNSS receiver works. So the very first thing is, to be able to see the satellite signals, you need an antenna. So your antenna will receive the signals, and now you have some high-frequency radio signals. And the first stage you want to do is, your radio frequency front end will down-convert this to a baseband, and your analog to digital converter will take the analog signal to a digital signal, and you apply some signal conditioning. So let's say there's some weird interferences happening, or there's some out-of-band interferences coming in. But the idea is, after you've done this first initial stage, you went from radio frequency signals have been sent to a digital version, and now you can start doing digital signal processing, and this is where the receiver really starts. So the most important thing in the GNSS receiver is the receiver manager. So this is the glue that just holds everything together. It tells what part of the receiver, what to do, how to interface, how to pass data along. So I just put this as a separate block to just keep in mind. I don't want to connect to all the sub-blocks to see what it is. So now we have our digital signals. And the first thing we're going to do is your low-level processing. So here you have two stages. So the first is your acquisition. And the idea here is, you're trying to find which signals are out there. So maybe you're indoors and you can't see any satellite signals, or you're outside taking a hike, walking, and you have open sky and there's many signals there. And the purpose of acquisition is finding which ones are there and just get an initial estimate of what is the frequency offset you have from the Doppler between you and the satellite, and some time offsets as well. Once you have acquisition, you would pass this over to a tracking channel. Now, the big difference between the two is acquisition looks at all possible combinations of a signal. Where tracking, you try to, instead of looking at the whole search space, say, I found my signal, but I want to refine how well I'm tracking this time delay and this frequency offset. This is why they'll also so another term you'll see is they'll talk about fine, of course, acquisition and fine acquisition, because the one is just much more precise.
Ross, just
so once you've done this, yeah.
Just a question on that. Now, when we are doing acquisition and tracking, correct me if I'm wrong, but it is also helpful to the people that are not into the GNSS. We are talking about in the input of acquisition. Are we talking about a digital signal? No.
Yes.
So we are still in the digital domain at this point. We are already in the digital domain after the front end, basically. Yeah.
Yes. So the output. So you're starting with the digital raw IQ sample. So this is typically very high rates. I would say a good receiver bandwidth is something be in the range of 10 megahertz. So this is 10 million samples coming in each second that you have to process. But then after acquisition and tracking, you'll have a very small number of measurements, basically telling you just what is the time offset and the code phase offset, which is a bit more correct here, and frequency offset. So you go in with raw IQ and you come out with observables and some measurement of the signal. Now, the next stage is, okay, we've got these, what do we do next? Now, your GNSS signals transmits a navigation message. So the first step you'll try to do is decode this message, because once you decode it, you can see what is the satellite's health, what is the satellite's position. So in this message, it explains some way of calculating the satellite position. And this is very, very important. So once you know the satellite positions, you know the times, you can start doing all these equations to find your position. So your message decoding has a lot of really important information you need to be able to do all the other processing. And your message, so your satellite position, together with your tracking results, you'll be able to calculate your pseudo range. So the pseudo range is this range between yourself and the signal. But because you don't know exactly where you are yet, it's not a true range. This is why we differentiate between a geometric range or a geo range and a pseudo range. Pseudo range still has some offset that you have to try to figure out later on.
Yeah.
And at this point, we're very, very close to telling ourselves where we are in the world. There's still one more step before we're getting there, and that is corrections. Now, there are a lot of things that go wrong in GNSS. And one of these are, for example, as your signal is coming towards you on Earth, it goes to the ionosphere, it goes to the troposphere, and all of these delay the signal. And you have to know how much is being delayed so you can correct this. But there are also other corrections. For example, as your signal is traveling towards the Earth, your Earth is rotating, which means it actually slightly moves further than what it would have if everything was stationary. So now you have to compensate for this relativistic movement of the Earth rotating. apply all these few pseudo ranges, and then finally, if we have our clean, nice, good pseudo ranges, we can go over to our position, velocity, and time calculation. So this is really the last stage and the heart of a GNSS receiver, where we've done all this processing, all these approaches, and now we know where we are, how fast are we traveling, and what our time is. And knowing the time is really important. I think usually when you think about GNSS, you think I'm driving somewhere, I want to know on which street I am. But a lot of people use time to know exactly when they are. So if you're currently you're probably watching this on the internet, or you're definitely watching this on internet. Internet kind of breaks down if there's no time synchronization between servers. And this is one of like the hidden places where GNSS does play a big role, and understanding it's more than just positioning is really important.
Yeah.
Matteo, I would ask you, is there any one of these points that you think needs a little bit more background? Or
I had to be honest, Ross. I think this is one of the quickest and complete at the same time presentation I ever seen on how a GNSS receiver works. So I think that all the boxes are quite clear at the moment. I would say go on in case I can ask later some questions.
Perfect. So the important thing is, once you have this diagram, you have a good idea of all these blocks and what they are. The really big question now becomes, where would machine learning fit in?
Exactly.
So the naive approach is, well, just take one of these out, put in an ML algorithm, and see if it does better than what the current state of the art is. And this is a good approach.
I can imagine that there is some papers of some guys that try to replace this with a neural network somewhere. I mean, just throwing.
You could. And I think the really big take-home message here is, we'll come to this a bit later as well, is so there are a lot of places where ML can play a role in GNSS. But ML really lags if you compare to other fields. Like if you look at computer vision, they are decades ahead with using ML compared to GNSS. And a lot of that is our problems are very well mathematically defined, which means they're very easy to solve with the optimal mathematical algorithm. So to then go and try to convince an engineer, hey, we have this algorithm that is perfect, has been working for 40 years, please replace us with ML. They're always like, no, very skeptic. Why would you do this? So it takes some time, but it's definitely changing.
Before delving into the ML application in GNSS, I want to spend some time to clarify a bit better the input-output relationship of our ML models. Specifically, the output will be clarified later during the lecture and is related to the application. But the input, as we will see later, are in most of the case what is called the IQ data. So explaining what is an IQ data is basically the target of this slide, and is mostly for the non-GNSS expert. So as you can see here below on the slide, you can see the scheme that Ross pointed out, a receiver scheme. We have the antenna that take the received signal, the radio front end we transform and process this signal and digitalize this signal, and then we have all these boxes here managed by the receive manager that basically aim at providing the position, velocity, and time delay. So if we zoom a bit better now on the radio front end and silicon conditioning, we can see here a really simplified scheme of how this works. Again, this lecture is not about how a GNSS receiver works. It's mostly to understand what is the input that we will use later on the models. So as you can see here we have our RF input, so the received signal. And what we do basically is we digitalize this signal with the ID converter, and then we apply to this signal what is called an IQ modulation. Basically, the same signal is multiplied with a sinusoid and a sinusoid in order to get, at the end of the day, a complex signal. So not all the GNSS receiver use this kind of modulation, but the most modern one use it. The reason why this is used is not the scope of this lecture. It's mostly for efficiency purposes. But what is important for us now to understand is that at this point, these I of t and q of t, which is our in-phase and enquadrature signal is what our model will take in input. So basically what we use as input to train and then to perform the inference. On the part of the slide here on the right, you can see a really simplified scheme. So we have the satellite transmitted signal, we have the receiver signal, we have the radio front end, and then these IQ signal are used by the ML model to produce the output we want. And of course, the nature of the output is completely related to the application. I think that now is a bit clear, so let's go and see the application of the ML in GNSS.
So if I look at this diagram, there are three big applications or three big approaches in ML and opportunities that are currently happening in the literature, and also see people doing it at conferences. And I would summarize these three as resilience, multipath, and adaption. So we'll go through all of these one by one, talk a bit more of what does it mean, where does it fit in the chain, and what people are doing there. So for the first one, we'll look at resilience. So this is a topic where I come from, where I've done most of my work. It's also one that I'm most passionate about, so we give much more information. But the idea here is we want GNSS to work. You don't want to be driving on the highway and suddenly you have no position at all. And now you're panicking because you have to take the next off ramp and you have no idea where it is. You want it to always give you position. So you want to have high integrity. You want to be robust against any interferences or outages. So this is where resilience is really how can we make it as reliable as possible. So if we're talking about resilience, I've highlighted some of the blocks here. So most of the work I've seen by far is on the signal conditioning. It is also one of the block boxes where you see the most ML currently in GNSS. And the reason why I signaled this one out is it happens before the GNSS processing. So it has a massive impact on GNSS, but it's not formally part of GNSS. The other three blocks is acquisition and tracking. So this is really low-level processing. And then finally, in your position domain, again, if you get your position, velocity, and time calculation. I made these yellow because there are approaches there. It's not as prominent as in this first red block. And I'll get to that on the next slide.
So I can imagine, Ross, here, the color is proportionate to the, I would say, how much you can use ML in that specific block. And then method decoding, pseudo-range determination, and correction is basically where is not used. Is it correct?
It's not used. I would say it's dangerous to say it's not used there. I'll probably say, yes, definitely, they'll never use it there. And then tomorrow, someone will send me a link and say, hey, have you read this paper? So it's not impossible. But definitely, if you look at where the research is happening, what people are doing, it tends to be grouped in these locations in the receiver.
Perfect.
So now the question is, what is resilience? What am I really talking about? So in resilience, the first thing that we really talk about here is interferences and jammers. So interference sources, is the bigger term here. So interference is anything that's transmitting a signal that's reducing your GNSS signals. And jammers is the same thing, but somebody's purposefully doing this. And what makes this whole thing difficult is some interference sources may be there, but not all of them. So the really classic approach is this distance measurement equipment, DME. So if you do drive close to an airport, you might see one of these big antennas, and they transmit signals in the L5, E6 bands. Now, these do interfere with GNSS, but they may be there. They are allowed to transmit. They're also a allocated user of that frequency band, which also implies if you happen to live close to an airport, you could be having some GNSS problems. That said, many of these DMEs are also designed to have minimal impact. So if your GNSS receiver is well designed, there's correct filtering and signal mitigation implemented, it should not be that much of a problem. The second one that you might see here is military type jammers. So this is when the military does have allowance to be jamming signals for reasons. So if you do look at signal frequency plan allocations, there's just like this thing that they list all the users for a specific frequency range, who may transmit there, who may use it. And then there's just like this ominous last column that says military ? Where they might be, but I think practically this is very rare. Unless you are living in very, very close to a war zone, it's very unlikely to have this event. And then finally, we have what we call privacy protection devices. Now, this is a slightly older picture. So a couple of years back, you could go onto Amazon, you can buy one of these, and it interferes with your GNSS signals. please don't do this. This is illegal. Even if you can buy one, it's illegal. It's better now, meaning that it's much more difficult to buy one of these. You can still buy them, but then it's under pseudonyms and weird things that if you read between the lines, you know what it's doing. But please don't buy them. Now, the use case here and why this is actually a issue in Europe is if you have somebody in a car, and it's a company car or they're a truck driver, it's obviously a company truck, and they don't want to have the company tracking them knowing where they are. And this is why if you look at these three at the top, they fit in the cigarette lighter of your car. So the idea is people put it into the car, you can no longer track the car, so now they can drive where they're not supposed to be driving with the car according to the company. So this is actually a problem we want to find and remove these. And all three of these cases, they interfere with GNSS and we want to deal with it. Now the question is, how do we do this? And what can we really do against these type of bad signals in the same frequency band as GNSS? So the first one is to detect. So this would be very basic supervised machine learning. You'll do some pre-processing. So you have your IQ samples coming in, and then you have some decision that says, is there a foreign signal in here or not? So in the typical use case, people will use something like a random forest or SVM here, but vanilla basic decision classification tasks. And the idea here is, if you detect, you can say, hey, there's a problem. My receiver is aware of it. Or if you're a bit more smart about this, you could call the authorities and say, hey, somebody's transmitting, come check this out, which is the correct action. So if there's any permanent interference, there are in each country some authority that has the mandate to go find them, remove them, or even worse, give them a very big fine. So yes. So the next step is, instead of detection, you can also do classification. Now here I have some different types of signals. So what you'll see here is each one of these graphs, you have a frequency. So this is somewhere in the middle, you'll have your GNSS signal, and you're receiving a very strong signal, and then you have your time axis. So this is going over time. You can see how your signal is generated. And what's important is, on this first slide, I showed this DME signal, and then I showed this military jammer, and then I showed this privacy protection device. Each one of those transmits slightly different signals. So one of the classic ones is the PPDs tend to transmit these chirp-like signals. So if you know exactly it's a chirp-like signal, it's easy to say, there's not just interference, but I know what type it likely is. So now I can say, it's interference. Or if I can detect that it's DME, I can say, well, it's not interference. He's allowed to be here. Don't call the authorities. This is legal. And then based on how these signals look like, you can really go. This is a super hot topic currently in GNSS. There's, I think in the last year at almost every conference, there's one or two papers just looking at this classification problem. And this is usually a combination of supervised and unsupervised machine learning. So in the supervised case, there's usually some pre-processing with a convolutional neural network. So as you can see, these are nice pictures, which means all this fantastic, great body of literature that was used for decades for computer vision suddenly applies in a new domain. And which means it just like scaled very quickly. Like, this is also one of the low-hanging fruits in GNSS machine learning.
So if I can understand a bit better on that, no, on the first, you said, because I've seen you do a separation here, detect and classify, you know, because I mean, on my, I would say, it isn't the same problem.
No. So I think if you do compare this to the more traditional or the wording in machine learning would say this is a single class classification and this is a multi-class classification.
Okay.
So in terms of that, it's very similar. The difference is, if you're only looking at detection, you can take a lot of shortcuts. Basically, you're saying, am I only receiving my GNSS signals and some noise, or am I receiving those plus a very strong signal? So you can do a very basic threshold detection. Yeah. The problem is traditional approaches do, like the most basic vanilla digital approach, traditional approach is an energy detector, which is just taking IQ samples in, squaring them to remove the phase information, and integrating, and if that's above a certain threshold, you detect. So it's a very easy problem. Yeah. Classification is much more difficult, because now you have to think, is there a frequency offset, is a time offset? How close? So I think one problem you can see here is this is a pulsed noise spectrogram. So you have a pulse of data, and then it's on and off. and you have a chirp. And this chirp basically changes frequency slowly over time, or fastly over time. But if this is changing faster and faster, how do you distinguish these two from each other? Like, where are those boundaries? And it might be that your receiver doesn't care what type of signal it is, but it does care that there's an interference signal.
Okay. I got the point. So here, what we're seeing here on the picture is basically, I mean, on the x-axis we have the frequency, and the y-axis we have the delays. No? Yeah. Sorry.
No, it's not pseudo range. This is the raw IQ sample. So this is before acquisition and tracking. This is still IQ values coming in.
Okay. Gotcha.
The problem is these data disrupt acquisition and tracking. So you have more noise in these. In the worst case, you cannot do tracking and you can't do anything in GNSS. In a medium case, it's degrading tracking so much that you have really noisy pseudo ranges coming out. And then your position just degrades. So what you tend to see in the interference case is you'll have a really good position, and then as interference power goes up, your solution gets worse, and then suddenly it's gone, and your receiver cannot say where it is.
Okay.
So I think the dark horse here is the unsupervised ML in classification. So one of the problems we've looked at in the past is what happens. So it's nice. So you say, oh, I have 5 types of signals. I'm doing some classifications. You do some supervised learning. And then somebody decides, well, we know everybody's using these type of signals. We're going to use our own distinct new type of signal. So can you detect a new class and incorporate those? And this becomes a really interesting problem. So at what point do you say, I'm very certain there is a signal, but it doesn't look like something in my database, and I have to create a new class for it? And this is actually a really big problem if you're really trying to find interference signals. So what you'll do in a live system is try to find these new classes and then give them for a human to look at. That they say, okay, no, in fact, it's still part of another class, or, wow, we found something new. This is a problem. We have to address this. So this is one of the few places where we'll see unsupervised learning popping out.
Okay, and you see kind of space for development in that part.
Yes.
Perfect.
The next problem is we know there's interference. We know what type of interference it is, but now I want to know where is it. So if I'm a standalone receiver, I don't care where it is. But if I'm the authority that says somebody's transmitting, they should not be there, let's go find them and switch it off and give them a fine, you have to locate it. And this is a really interesting problem. So one of my former colleagues, Dr. Tobias Feigl, he did this crazy thing where he used a auto encoder to encode these informations from different receivers, get them all together in a database, and then when he decompresses it, instead of decompressing it, uses the latent space directly to do some positioning. Really crazy stuff, and it worked really great. But this is, a bit more difficult. So now we start looking at regression type tasks. Usually you have to do this more with supervised ML as well, just because it's a very difficult thing to achieve.
So sorry, in this case of the autoencoder, can you specify a bit better what was the input of your colleague used in this case?
In his case, it was actually a number of features. So part of the features were the raw IQ samples going in, some pre-processing and then going in, the same as the previous two. And the other features were actually from later stages in processing, which was looking at the carrier to noise density ratio coming from the receiver. So basically, each receiver is estimating how good is it tracking a signal. And if you have a lot of receivers together, and some of them are saying, wow, we are tracking our GNSS signals great, and another receiver say, no, I'm struggling a lot. Okay. Then likely it's very close to interference source. Or it's indoors, which makes the problem much more difficult.
I got the point.
So you have to first detect, is it interference, or am I indoors, or did somebody switch my antenna off? So this is much more rare. I think using ML to locate interferences is a bit more rare compared to the other two cases.
Sure.
And then we get to the last one, which is mitigation. So the idea is, so I showed these graphs earlier. So this one is just put to the side. So you still have your frequency. And you can see your chirp signal that's changing over time. And the idea is, if I can find out where the signal is and remove it, then I can remove the impact for the rest of GNSS. So this is, if I'm in a standalone receiver, I cannot navigate. All my signals are suppressed because of this interference source. But if I can remove the interference, I can navigate again. So there are two approaches here. So the one is, once again, doing some regression tasks. So the idea is you just pass all the IQ data in. ML does the interference mitigation, and it pops IQ data out again. So this is very much like removing background people in photos. It's, I would say, is the closest equivalent if you look at adjacent fields. But this tends to be really challenging and really difficult. And the main thing here is, if you look at any adjacent fields, your noise in the background is what you want to get out. Like you usually do some filtering to remove noise, and you know what your features are, and you like want to pull them out. In GNSS, it's the other way around. Our signals, because of how they're developed, are underneath the noise floor. So you don't want to disturb the noise. You want to keep the noise as it is, but anything that's poking out of the noise you want to take out. So it's the reverse of the typical image processing media processing ML.
I got the point.
The other approach, and this is something I've also been playing around a bit, is if you start looking at reinforcement learning. So the idea here is there's a lot of really great mitigation algorithms, traditional approaches, and they work really good. The problem is we have different types of signals. So some mitigation algorithms are fantastic against chirp signals, but they cannot mitigate other types. Or you have mitigation algorithms that are great against pulse signals, but they cannot work against a chirp signal. And what you'll do is you'll use some classification first. So you'll classify what type of signal it is. And then based on the signal, select which algorithm is going to mitigate it. So you basically, instead of making the AI do all the work, you just say, well, you're on control of running the receiver and doing all this pre-processing. Which block should be switched on and which block should be switched off? And yet it's interesting because you can do this reinforcement learning where you see what's coming in, what's coming out, and then change the well-known traditional mitigation algorithms, whether this is tuning some thresholds or switching them on or off, and thereby optimizing the whole output. And this is something I think will be really exciting in the next couple of years. I've seen very few papers about this. So now I can go on to the next one, or the next problem. This is spoofing. Now, spoofing is also somebody transmitting a signal, which is wrong. But instead of transmitting an arbitrary thing trying to disrupt GNSS, you try to transmit a fake position. So the idea is you capture a GNSS, and instead of your receiver saying, I'm driving on this road, it suddenly tells you, no, you're driving on the other side of the world. So there's this very nice report a couple of years back where all the ships were spoofed, and then suddenly all the locations were on top of an airport close in the Black Sea. And this is the typical case where you say, like, oh, suddenly you cannot trust your GPS because everything's broken. But the most, like, my favorite spoofing ever is still Pokemon Go. And the reason is, for decades, people are saying spoofing is possible, we should be ready for this. And it kind of was, and it was like slow changes until the summer that Pokemon Go came out, and teenagers decided, you know what, I'm going to spoof my phone because I don't want to go for a walk, it's too hot outside. And then just suddenly spoofing became much easier, like because there's hundreds of teenagers trying to break this problem, it just developed much faster. So the idea here is you'll sit on the couch, spoof your phone, and your phone thinks I'm taking a walk in the park somewhere catching Pokemon. Meanwhile, you're just on the couch doing nothing, which goes against everything the game tries to do.
Yeah. I can imagine.
Now, spoofing is much more difficult. So now, because you are sending something that's very much like a GNSS signal, doing it on the IQ data is much more challenging. So typically, this is where you start looking at your acquisition or tracking approaches and where are they, how are they responding to it. So the question is, how do we look at spoofing, or where does ML fit in spoofing? So the short answer is it's the same four things. Yeah. You try to detect it, you try to classify it, you try to locate it, you try to mitigate it. Like it's the same four steps. It looks a bit different. And what I have here is actually two of the work that I've been doing previously. So the idea is, so the problem I was working on is if you have a spoofing attack and it's really well done, what tends to happen is you have all these satellites spread all over the sky. So if you look at your sky plot, you'll have satellites in all directions above you. But transmitting those signals from the sky is really challenging. So typically you have one guy transmitting on the Earth a signal towards your antenna. So then suddenly all of these satellites are clumped in one direction. So even though this satellite number 20 is telling you, no, it's over here, which is the correct place, it's at the same location as all the others. That's a horrible example. 32 is telling you it's over here, but in reality, you're receiving it from one direction.
Sure.
So here we have one example of a confusion matrix that was trying to do this classification of different spoofing types. So what you'll see here is in the first column, I have an authentic signal. So this is if all of them are unspoofed to real constellation. And all the other columns are different spoofing attacks that I've simulated. And generally, you can really, looking at the spatial information, really well distinguish or detect or classify the spoofing attack type. So there's one exception here, which is, we'll take a lot of detail to explain why this happened. But what I can say here is that these two spoofing attacks are really, really, really similar. And the way to find how they differ is challenging. And this is still an open problem that I'm trying to figure out how to do better. To just show that ML does exist in GNSS with some confusion matrices in a good place.
So, sorry, here you're trying to identify if your signal,
Yes, the signal
is authentic, it comes from a satellite.
Yes.
Isolated means that you are a spoofer.
So all of these are different spoofing attacks.
Okay, got it.
And the nuances between them is so isolated attack. So this is a very, very harsh attack where you're basically placing a tin can over your antenna and it only sees spoof signal. There's like no competition to the other signals. And then all the others are some version where your receiver receives both, and sometimes it tracks the one, sometimes the other. And now the question becomes, how good was the spoofer? One of the issues here is the more money you spend on developing a spoofer, the better it is. There are some, I would point you to some GitLab repositories where you could do this at home, but once again, this is illegal. Please don't do this. Or other YouTube videos where people explain how to do it, but once again, it's illegal. Please don't do this outside a lab, which tends to be really cheap attacks, and they're easy to identify. But it's a trade-off, like what type of attack it is kind of tells you what the person's budget is. And if you know what their budget is, you know, is this probably somebody playing around Pokemon Go, or is this likely somebody I should be worried about?
Yeah, I got the point. I got the point. I think the results here are quite promising if I look to your confusion matrix.
In this case, yes. This was one of the better results I cherry-picked. And also, in this case, I'm also using an array of antennas, so not just one antenna, but multiple antennas, which is really expensive. So the average user will probably not do that, especially if you have a mobile phone and you don't have an array of antennas on there. You have one. If you're
in this case, you mean an antenna to make the spoofer.
No, so this is for the receiver.
Okay.
So the receiver has then multiple antennas and has multiple options.
Okay.
To look at the signals.
Perfect.
And I believe that should be the end. Not the end. Almost the end of spoofing. Now with spoofing, it becomes difficult. So here you see ML. Some people do try like just pushing all the IQ values into some classifier to try to detect and classify your spoofing attack. So this would be a pre-correlator attack or pre-correlator architecture. And then many people do the post-correlation. So this is also what I did. So you're basically using your tracking and acquisition blocks, and them do their processing first. And once you have results from acquisition and tracking, you use this for your detection. And this is a very big topic when you're talking about spoofing is the pre-detection allows a lot more for ML to do. Like you can do really crazy deep learning things, but it's a lot more effort, a lot more difficult. Where post-correlation, you're leveraging all the benefits GNSS already developed over the years, but you're also limiting what you can do with them. And then the last thing with spoofing is ultimately one of the best things with spoofing is sensor fusion. So you could fake your GNSS, but it's difficult to fake other sensors. So if you take a very basic case of trying to spoof your phone, you could tell your phone you have the wrong position information, but you still have inertial navigation inside your phone, which is telling you the phone is not moving, but you are telling it it's moving. So suddenly the two sensors diverge. One of the best approaches, and here a lot is happening in GNSS, but I would limit this outside the discussion for today.
Is there some research that is interesting research is coming out of that branch?
Definitely. So the sensor fusion itself, what I've seen most papers in spoofing detection with sensor fusion is they tend to go for traditional approaches. There are some on machine learning, but they're not as many, but I do expect this to change a lot. Where this becomes really exciting is when it's not just GNSS plus inertials, but if you're doing this plus 5G positioning and vision, and you're basically having a suite of things coming together, which is when we start talking about stuff like autonomous driving. And at that point, it gets really interesting, but that's also many of the people who, because of protecting their product, will not tell you if they're using ML or not for safety reasons.
Okay.
But yeah, at that point, we're so far out of GNSS, I think.
Yeah.
It's a bit more difficult to explain.
Absolutely.
Or justify. I think that should be the end of resilience. So the next topic is multipath. So with resilience, these are, I would say, anomalies. Usually you do not have this problem unless you live in an unfortunate area where you have a lot of spoofing and jamming and interferences. But multipath, every GNSS receiver is affected by this to some degree in every application. And this is a much more common problem. It's not as severe, but it adds up. And I think this is one of those questions where do you want to have a massive problem that happens once and never again, or do you want to have this constant issue that you have to deal with? And this is the multipath case. So looking at multipath, the layout is a bit different. So definitely a lot of work is being done in the correction side. So can we correct this multipath error on our pseudo range? And in the PVT, so can we exclude a satellite from the position calculation or de-weight it or make it less of, so if there's one satellite that really has a big problem, put this to the side and rely on the others. And then there are some techniques in tracking. And I'll get to them as well. So the question is, what is multipath? And I think here we can explain a bit longer what it is. So what you need to know for now is if you have your signal directly coming to your receiver, you would have this very nice, beautiful triangular correlation peak. And I think that's all you need to know. Like if everything works correctly, you have a triangle.
This is the paradise.
Yes, and this tip of this triangle relates to your time delay that you have from your satellite. So this is the thing that's really telling you what is the delay between your receiver and your satellite with a lot of additional information. But the problem is, if you have this car between buildings and you have another satellite which is not as ideally placed, you would have first a line of sight which will be hitting a building. And because it goes to the building, it loses a lot of energy. So you still see the signal, but it's low, like you have a smaller triangle. Even worse, you have a multipath reflection. So you have the signal sending out. You have one signal coming from bouncing off of a building. So if you're used to computer games and ray tracing, this is ray tracing, but bad ray tracing is a way to explain this. So now you'll see we have another triangle. And this triangle is a bit bigger because it has a nice reflection surface. It's not being attenuated through this building. And then we might have a third one. Now, a 2 bounce, without going into too much detail, tends to be more severe than a 1 bounce in GNSS, and this has to do with the polarization of the antenna. So every even number of bounces or reflections have much more gain coming through of the antenna itself. If it's a good antenna, if it's a bad antenna, other way around. So now I have these 3 signals. I have my very bad attenuated line of sight, and I have 2 non-line of sight reflections. If I add all of these together, I will get some weird curve. And suddenly, this nice triangle is triangle-ish, but you can see there's a bit of a delay happening here. So what your algorithm will be doing is it adds these 2 points near the peak, tries to estimate where this peak is, and in the ideal case, you'll have your peak on this triangle. In the non-ideal case, it will be on this new quasi-bad peak. And this relates to this time offset that's pulling your pseudo ranges away. And this is really bad for your positioning. So the question here is, how can we reduce this? To really show some impact here, here's a multipath example. So this is data from a Kaggle challenge from last year. This was the Google Decimeter challenge. If you're really interested in GNSS and you want to just start and see cool things, even though the challenge is fast, I really recommend to go look at it. Like, it's fantastic. There's a lot of resources, a lot of people helping out, and a lot of data to play with, especially if you're coming from ML and you need a database for reasons. Great place to look at. So what you'll see here is this is a route that's in San Francisco. They start at the bottom between big buildings, then get onto the highway, and then end again in some bigger buildings. Now, if you're looking on the right side, I'm looking at my horizontal error. So this is now, after I've done my position calculation, how bad is my position relative to a reference position? So this is how big my error is. And what you'll see is, at the beginning, between the buildings, there's a massive error coming in. So we went here from 7-8 meters errors to some as big as 30 meters. And then at the end, we see massive spikes coming out. And here we have an error up to 120 meters. So if you're thinking I'm 5, 6, 7 meters accurate, and then suddenly you're on the other side of the block, not the other side of the road, 120 meters is the other side of the block, your Uber won't find you. And this is the effect of multipath. So the question is, can we really reduce this? And there are ways. So this is, I do have data where I did some applications trying to minimize this, but I think that will be a very long detour discussion about multipath depression. But now we know a bit about multipath and how it looks like. Where does ML fit in here?
Yeah.
So the first one is detection. To just say, I have some satellites that are great. I have one satellite that's horrible. I detect multipath, and I say, don't use the satellite for positioning. It will degrade my position. Just throw it out. It's garbage. Do not use this until I've moved away from a building or some issues. So this will be a basic supervised approach, and just flag, don't use it. Which sounds great, right? If you're thinking I have all these great satellites and one bad satellite, throw one out. Good solution until you're in the middle of a city, a big city, and all of them are multipath. And now the question is, well, if all of them are multipath and you're throwing them all out, you can't do any position. So then a bad position is better than no position. And this is where position weights comes in. So now you're doing some regression task where you're trying to limit the errors. You're trying to say, well, I know it's multipath, but I trust this multipath satellite slightly better than this multipath satellite. And you're basically trying just to bargain for your life to have some version. So this will typically be some supervised approach. There are some feedback approaches if you want to do reinforcement here, but this is a bit more complicated. Very popular approach as well in the literature. But a better approach, if you want to spend much more time in your ML, is to start correcting it. So the idea here is, we know we have some error, but can we estimate what this is? Yeah. So if we have enough information about this peak, could we try to figure out what the correct peak is and try to pull this back? So this is what we'll call this will be a regression task, also supervised or reinforcement learning in this case. And if you have more information about your surroundings, so here is something that's from GPS World, where you do this map where if you know how your buildings are, you have some 3D values, you can try to figure out where were these rates. Like, can you reverse engineer, figure out where these multipath could have been and kind of de-interleave them. And then you get these really fascinating maps where you can try to say, well, likely I'm closer to this building or not. So this is called shadow matching. And their ML approaches are amazing. So this will be the great one of trying to figure out some improved positioning. And then a small point here is to get this triangle is not as easy. It's not trivial. Most receivers try to limit processing. So you only have 1 or 2 samples on this triangle. So then to be able to correct this, you'll need more information. So this is where multi-tap correlators or strobe correlators comes in, but then you have a much more expensive receiver. So there's always this trade-off of, you could solve this problem by adding a lot of more processing and effort onto it. Do you have any questions? I think this is, a much more user-friendly application than the previous ones.
Absolutely. No. I was just looking at your map here. So basically, if I'm trying to interpret it, the shadow map. This is the output of our ML model, no? What this
yes.
Case. And this is a 2D map, so you have X, Y, R, east and north, and the color indicate the...
It will be a weight.
A weight, yeah. Of multipath? No, sorry, in this case...
of the receiver being at that location.
Oh, okay, sorry.
So in this case, well, it's either receiver being at that location or given the pseudo range and the information you have about this, that it's likely there. So if I know, let's go back to the slide. If I know at this point, I have a very strong likelihood that if the satellite is there, that I'm pushed away from this building because of all these multipath effects on the side, then you can start saying, well, likely I'm closer to this building in reality than what I am. And this is what this thing's trying to tell you, like your pseudo range should be more in this direction because of multipath and not the other way around. And trying to figure out how, in which direction you're much more likely to be in.
I got it.
So one of the position techniques is you'll do a map like this for each one of your pseudo ranges and then put them over each other. And then where you have a peak, say that's likely where my highest likely position is, which is a much more data-driven or a more, let's say like a testing approach, as opposed to just the vanilla least squares solving for positions that we use in GNSS.
Yeah, I think we can go on the next. I think you have another one, no? The adaptation.
The last one is adaption.
Adaptation, sorry.
Adaption. So the idea here is, so what I'm trying to do here with this very, very basic curve here is, as you are going around the corner, how good can you remain in track to be there? So the green one would be really tight to your ground truth, and then the red one is basically losing lock. So a way to explain this is, well, let's look at the
our reference.
Our reference. So once again, there are two blocks to use this. The one is if you're tracking your signals or if you're tracking your receiver. So both of these is you're using past data, you're trying to see where you're going and how do you put them together. So once again, signals will be low level, positioning or your receiver will be high level. So a typical approach here would be something like a Kalman filter. So what a Kalman filter does is it tries to estimate your position based on previous values. So you'll start with a position where you are now. It will make a prediction what would be, so this will be the blue car. It will take new measurements, which will be the red car, and then based on these two, try to fuse them together to have a good estimate of where you are. So you're using the past, which is blue, you're using the current state, which is the red, to improve your measurements, which is green. And now the question is, oh, this is fantastic. So in the background, you have some Gaussian model that tells you how likely these are, and this results in a new one. Theoretically, this is the best thing you can do, but do you know how this error distribution really is? So do you really know how accurate your predictor is? Do you really know how accurate your measurements are?
Absolutely.
And one of the things you can do in a Kalman filter is to do some kind of reinforcement learning where you try to figure out, I think my noise level for this satellite is so much. Can I improve it, reduce it, and adapt how much? So basically, how much am I trusting my blue car? How much am I trusting my red car? And getting this a bit more in balance is one of those cases where you can do some recursive machine learning coming in. Another option is here is when you're predicting your car, you have some model in the background. So if you are not moving, the best model is to predict that I'm standing where I was standing the previous time. But if I'm in a car, I'm predicting I'm accelerating at the same pace I was last second, in the same direction, in the same way, which is good until you get to this corner, and then suddenly your whole model breaks. Absolutely. And can I swap from one model to a different model that maybe considers how to go around a corner? So basically adapting these algorithms are already there, like how can I change my weights, how can I change my model? Similar to the tracking loop, so the equivalent here to adapting the weights and tracking loop would be doing the loop bandwidth. And here I have a great example. So this is from a paper one of my previous colleagues wrote, Inigo Cortez. And what he's doing here is he's got a very rough path. So he starts with the receiver, and then he just runs in one direction and then does a 90-degree turn in the next. And he does as difficult as possible dynamics and see, can I still track my dynamics as good as possible? Now, the first 600 seconds, he's not moving. So this is where he's basically on 0.1. And then he just starts running and change all directions. And each one of these lines on this right graph is a different satellite. And this gamma function here is basically how much it's trusting the values in that function. So how agile or slow or precise you are. And as you can see, each time there's like this corner, it just says, well, something's happening. Open, we need to adjust our model. Does this, and then as it gets more confident, say, okay, we can pull back in, it looks safe. And then as it gets to the next corner, it says, well, something happened again. And it tries to adapt all these algorithms in the background. So he's currently working on concepts like this using some reinforcement learning. And this is really exciting because now you can actually start saying, I have an all-purpose receiver that kind of knows, am I standing still? Am I running around? Am I in a race car? Am I in a rocket? And it figures out what to do, applies the best model, applies the best weighting, and goes on from there. And this high-level decision-making is just making receivers more general purpose than what they would have been before.
So can we say that in this case is doing like a noise estimation? Is the wrong thing?
Yes.
Okay. So in this case, it's estimating the quantity of noise at the receiver, so at the state observer in this case of the Kalman filter, no?
Yes.
And so when he said that the variance of the noise in this case of at the state observer of the Kalman filter is go too high, he said, no, block. There is some inner logic that kind of try to mitigate that in the Kalman filter, or maybe like a post-processing or pre-processing of the Kalman filter.
It's very close, very close. So what this gamma function is, so a bit looking behind the curtain what's happening, is this gamma function is actually a trade-off between noise and dynamics. So the idea is let's say you have your common filter and you have all your measurements, and suddenly you have this outlier.
Yeah.
And your first question is, okay, is this just statistically a fluke? Like, should we filter this out, or I'm suddenly accelerating, and this is actually my new dynamics?
Yeah.
And you have one sample. You say, well, likely because of the past, this is noise. And then you see your second sample that's also high. Like, okay, no, 2 in a row, it's too big. We really have to reduce our noise model and accept that this is new dynamics and change what's happening in the background.
I got it.
And this is what the Scrum is trying to do. It's like trying to finding this trade-off between what is my noise model, what is my dynamics model.
I got the point. Yeah.
And if you do this, you recover much quicker. So a couple of slides back, I showed this triangle of multipath. So one of the big problems in GNSS is, as long as you're close to this triangle, you will have a great day. Tracking will work. You'll have some pseudo ranges coming out. Everything's good. The moment this triangle is moving away from you and you're not following it directly, you're buried in noise and you lose it. Then you have to go back to reacquisition. You have to try to figure out where it was. It's a drama. So the faster you can adapt and figure out if it's moving away or I have to keep with it, the better.
Okay. This is really interesting, this one, yeah.
So then we get to I talked about the 3 big ones. So this is resilience, multipath, and adaption. Now the question is, are there others? So I think putting 3 big groups here is oversimplifying the problem. And I think there are some honorable mentions that we do have to go through to really say, but you know what, there's a lot you can do. I'm still skeptic about some of them, but I also know, give it 2 years and someone will have a fantastic solution to solve something there. So it does change. The field changes very, very quickly. So now we can look at many of the others. So in this case, a lot of the places just light up. I think one of the interesting ones I was thinking about was the receiver manager. So now we're using some state machine that says, if this happens, that does. Doing slightly more intelligent, like high-level AI in a receiver manager could be interesting. I haven't seen or heard this yet, which basically means that the current state machines work well. There's no reason to replace them yet, but it could be an interesting thing to do. And obviously, low-level processing functions, so your acquisition and tracking is good. Corrections are always a fantastic one from ML, and then your final positioning. So you have some options that you could be looking at. So one of these is, for example, I've seen a paper where people were trying to replace the entire acquisition block with machine learning. So basically just throw in IQ data, and what acquisition does, it does this massive correlation. And you'll have a single peak coming out at the correct frequency offset and your time offset. So this is this code phase I was speaking about earlier. And their idea was let a machine do it for you and see how it goes. I'm very skeptic about this because you do have good traditional approaches that does this very efficiently.
Absolutely.
But they had results. Another one was positioning. So I did show some things in the shadow matching and multipath correction about positioning, but there are also approaches to completely remove that. So you say you have some black box, some transformer model, some deep learning model maybe, that's replacing your entire Kalman filter, your entire weighted least squares, and it does its own thing.
With the IQ as input, or the...
As the measurements, so the observables as inputs. So you put in your observables, and then it decides what the positioning is based on those. So you could be doing this. I'm also very skeptic. Mainly because a weighted least square works great, Kalman filter works great. You need a lot of energy to put it into a different approach to really show, but can we replace this?
Yeah, absolutely.
Corrections, satellite clock errors, your satellite position errors, your ionosphere. These are classic regression tasks. There have been some approaches like this, worthwhile to look at. An interesting one would be something like cycle ambiguity detection. So a small background here is, so I was speaking about the pseudo ranges you're calculating, so how far you're off in the satellite. Now, your pseudo ranges are noisy, they're good, but they're not precise. If you use your carrier frequencies or your carrier signals phase, you're much more precise. But the problem is you have a ambiguity every time it repeats. So if you can resolve this, you have much, much better positioning. So this is usually when people talk about you have centimeter level precision with GNSS with RTK going through. The problem is the moment, if you can solve this ambiguity faster, it's much better. Or if there's a cycle slip that you missed, it just breaks your positioning. You have to go back to it and fix it. And this is something I think could be really interesting for ML tasks to try to figure out, can I detect a cycle slip? Can I fix it? And can I help RTK to be slightly more efficient? Yeah. Because ambiguity fixing is a bit of a nightmare.
I can imagine. I never worked with that, but I can imagine how.
Yes. but your reward will be a much more reliable, highly precise receiver. So
Yeah.
going from meter precision to centimeter precision, it could be very rewarding.
Also money-wise.
Yes. Scintillation. Without going into too much detail here, I've seen a lot of papers regarding scintillation. This is something I've never done. So this is far outside of my experience zone in GNSS. So a minor background here is, as your signal comes to the ionosphere, if there are anomalies or weird things happening, you have additional delays coming in, and this disrupts this triangle. So very similar to multipath, but not the same. But this is especially bad for carrier phase positioning because it just suddenly gives a burst error coming through. And there people have been doing some scintillation event detection and mitigation approaches. And then the last one I was speaking about earlier was, what if you do have intelligent receiver manager that's a bit more, knows what it's doing, trying to fix as much as possible where it can.
Okay.
And then many more. I think there can be many more things in GNSS that I haven't thought about. I think that nobody has thought about until it happens and changes the whole environment.
Of course, if someone is looking at this video, has some new idea, put in the comment or please contact us. I mean, I think that we'll be more than happy to say that there is something else that can be done. Ross, I think with that you have concluded your lecture, or do you have something more?
My last slide is blank.
I like this slide. Anyway, thank you very much first of all for the lecture. I've seen how much effort it is to explain some really complicated concepts like this to people that maybe has some ML background but not GNSS, maybe has some GNSS background but not ML. So I can imagine how much difficult it is, and I think the scope of this channel is exactly to fill that gaps between the different states of the AI, of machine learning. So first of all, thank you very much. I think you've been really clear, and given how much broad is the area, how much still in the kind of avant-garde of the research we are, there will be tons of questions for each of the topics. So I would say just focus on a more general question. On the last slide that you show, imagine that you would be a research group, but a researcher, not someone that's doing his or her PhD. What do you think, based on your experience, would you invest your time, basically, your time and energy? And you think it would be more rewarding in terms of visibility, in terms of how much you can impact with your research on that,
Mm-hmm. Well, if it's on this list, I think this is the others one, which is much more skeptic. I would actually go for a combination of these two. So this is the positioning and the corrections. And the reason why I say this is, one of the problems we have currently is so if you want to go really, really precise, the best way to become precise is to do RTK. So this is, you have some base station, you have your receiver, and you're calculating your differences between the two. So you're doing some relative positioning based on all the satellites. RTK works amazing until you're too far away from your base station, then everything breaks. You have different ionospheric things. So then you'll go over to something like network RTK, where you may basically putting all of these together, etc. Which is great. It's not as precise, but it's still good. And then one level further is if you're trying to do some PPP. So this is precise point positioning. And the idea is you're trying to estimate all these things. You put in some massive Kalman filter. You try to estimate your ionosphere, your troposphere, how wet or dry it is. Massive amount of estimation going in there. But the thing is, your PPP takes 20 to 40 minutes to converge, which is long. That's super long. If I can combine these two and I have some ML algorithm that can tell my PPP instead of converging in 20 to 40 minutes, I can converge within 2, I would go for something like that.
Okay. So I think this is a challenge open at this point.
Yes.
And okay. So thank you very much again for a
pleasure. Thank you for having me. It was great to have this chat with you.
Yeah, and I really hope that stimulate other conversation and also, suggestion. As I said, that this is a kind of open area, and there is so much we can do. It's something that Ross have not talked about. So thank you very much, and maybe next year with another lecture you can update me if there is some other stuff going on. Perfect. Bye.
Cheers.